Hello, I'm Santosh Devasya. I'm the General Chair for ACC 2020. I want to welcome you to this last day of the conference for our outcome. We have had 2 days of online meetings with more than 20 parallel sessions, where all things have gone relatively smoothly. This is our first online ACC, so we are all learning how to run an online ACC. So I'm very grateful to this incredible outcome to make this thing happen. We have several new innovations at this ACC. As in the previous days, we'll have online meetings today. We'll have virtual booths for sponsors, special sessions, and meetings. You can also communicate and form groups using Slack, see the conference website. And we also have NSF office hours today. One of the new things we have is the rapid interactive sessions in the mornings. We'll have them today as well. These are short talks that reach out to a large audience each day. And then these are followed by about 45 minutes of interactive discussion of each paper for about from 11 to 11:45. We also have the poster sessions for late breaking results during the coffee breaks. And you might have been familiar by now for using the online program. We have a tutorial on our website. And if you go to the program at a glance, you should be able to access the different sessions and the Zoom links through that. We have a strong technical program. And so if you liked any of the papers that you saw today, please nominate them for the Hugo Shaka Award. There's a link for this, and it's also on the websites. You can also nominate the best rapid interactive paper, and the links will be provided during the rapid interactive presentations. We have exceptional plenary talks, and on that note, it is my pleasure to introduce the morning's plenary speaker, Professor Lina. Professor Lina Lee is a professor in electrical engineering and applied mathematics at Harvard since 2014. And congratulations to her promotion to professor, which happened this week. She has a PhD in control and dynamic systems from Caltech in 2013. Her research interests include distributed learning, optimization, and control of cyber-physical network systems. She was a recipient of an NSF Career Award in 2016, the AFSOR Young Investigator Award in 2017, and the ONR Young Investigator Award. She won the ACC Donald P. Ekman Award in 2019. And so her today's presentation is going to be on distributed decision-making in network systems, algorithms, fundamental limits, and applications. So, Professor Na Lee.
Hi, everyone. It's my great honor to give this ACC plenary talk. I know this is a challenging time for many of us, so thank you for watching this video. I hope everyone stays safe and healthy at home. In this talk, I will discuss distributed coordination in network systems. Feel free to give me any feedback in any format. I've listed my email address here. And this is my first time making a video presentation. I have realized that it is very, very difficult to even just make an okay video. So please bear with me if there is any issue. Before my talk, I would like to get the most important message out. All the work I will present would be impossible without my students, postdoc, collaborators, and all the funding agencies. I'm very indebted to all the support I have, so I would like to take this as an opportunity to thank everyone. Also, I would like to do a small advertisement for my own group. The people I highlighted red here will be on job market, and the people I highlight in blue have been or are going to be tenure-track faculty. Everyone is wonderful, and I have learned so many cool things from them. So please watch for their names and their new work. Now I'll come back to my talk. In the past decades, we have seen major revolutions in the fields of computing and networking. As we look around, we notice that there are more and more connected devices. It was actually predicted by the end of next year, on average, everyone will have more than 4 connected devices. These devices have made us more connected. Even during the challenge COVID-19 time, so we have to keep social distance physically, we actually become more connected than ever before. We can join conferences anywhere, anytime in the world. We can set up social programs anytime, anywhere in the world. And I guess people who are watching my video already have more connected devices than the predicted number. These ubiquitous connected devices bring us a huge potential in boosting autonomous decisions for our daily life. Here are a few examples. A more comfortable but more energy-sustainable home, a more efficient but safer transportation system, a lower cost but more flexible and powerful manufacturing system, a faster response but more personalized healthcare system. Putting all this together, they outline a beautiful vision for our next generation of smart systems. Both research communities and industries have been working together to revolutionize our grid, our transportation system, our communities and cities, trying to build smarter ones, which are more autonomous, more efficient, more resilient, and better in improving our quality of life. But here is one question. Can we really make our system smarter by having more connected individual smart devices? What's the current status? When we look into the reality, it doesn't take long to realize that we are only at the beginning stage of transforming our systems to smarter ones. Here are a couple of examples. Last year in California, PG&E had to cut power to 1 million people in order to prevent the potential wildfires that was predicted by the hot, windy weather. And similarly, a recent mobility report done by Texas A&M Transportation Institute has predicted that we might waste more and more time in traffic. All this news point to the same issue. Having individual smart connected devices is not enough. We need to figure out how to coordinate, how to control, and how to make the best use of them. But the question is how. So now let's take a step back and to figure out what's going on with our system. I will take a control perspective. First, we have a physical network system that connects different sensors, and the sensors can monitor what's going on with our situation. And we also have actuators can react to different kinds of situations. Between the sensors and actuators, we can design good control policies to making sure the actuators can react to the information appropriately. So the picture fits into our classic control loop diagram perfectly. There are many new things hidden behind the scenes. Firstly, when we zoom into the picture, we see an enormous amount of active points, sensors and actuators. They keep generating real-time streaming data, leading to a massive volume of data. And people call it as big data. To handle the big data issue, a lot of research activities have been devoted into data processing, to large-scale computing. And we are trying to build advanced cloud computing and data centers in order to handle this massive streaming data. However, this is not just a merely big data problem. When we further zoom into the picture, we notice that all the active points are actually spatially distributed all over the place. So communication has become ubiquitous, but no matter what kind of communication technology we're going to use, we face different challenges, such as latency, limited bandwidth, package drop, privacy, security, among many others. It is almost impossible to just dump all the data to some powerful central place and expect a good solution can be computed and communicated to the local actuator quickly. As a result, distributed computing and control is almost necessary for coordinating all the devices. And one ideal picture is to let the devices decide by their own, like individual device can react based on their local observation. But it's not hard to imagine that this is not going to work because they lack coordination. So the next level is to allow the devices to talk to their neighbors. And depending on the infrastructure and the complexity of the problem, We could also include additional layers to allow hierarchical layering coordination among different regions. Lastly, let's come back to the system that we have been talking about. Because of the connection among so many heterogeneous components, the system quickly becomes very complex, which are very hard to model and definitely very hard to understand. Besides, the environment changes quickly, making the system never in a stationary mode. These challenges call for quick real-time solutions, calling for distributed real-time learning and control, and the goal to make the system react fast, and in the meantime, trying to be efficient, robust, resilient, and you can add properties you want. So in summary, all these discussions motivated the focus of this talk. How can we distributedly coordinate the devices? To further narrow down the scope of the talk, given the limited time, let's just focus on the local communication where devices can talk to each other. To recap, there is a physical network connecting individual nodes, and nodes have sensors, local processors, and actuators. They make local decisions according to their observations and communication among the neighbors. The goal is to design distributed coordination rules to make sure certain desired global behavior can be achieved. To develop systematic solutions, the approach we often take is to start with modeling the desired collective behavior. Here is a high-level abstraction of a typical network coordination problem. Say we have an agent, and each agent has a state, action, and we can use F to capture the global cost or the global reward. And G is a couple constraint, and C can stand for the local constraint. And here we also use delta to model the model uncertainty or the environment uncertainty. So once we understand the global objective, we look into the requirement for the local policies. Individual agents make local decisions based on their local observation and local communication. What should be local would often depend on the system infrastructure. As you can see, the problem setup is very much like the classic decentralized and distributed control. So of course, the classical result naturally apply. So people have known for a long time that the decentralized control in general is anti-hard. But as stated in most complex analysis papers, anti-hard doesn't mean the problem is untreatable. For many problems, as you will see in this talk, we can harness special properties for scalable solutions. But you might feel it more like cliche when I was saying harness special properties. Of course, everyone knows that we should take advantage of problem properties, but what properties? And how to start the procedure? So in this talk, I will give you three perspectives that we often take. First is the problem structure property, and then the system physical property, and lastly, the algorithmic properties. More specifically, I will present three concrete examples. First, we will talk about scalable reinforcement learning for general multi-agent network systems. Then we'll move to a more concrete system, which is a power system. And lastly, we will even move to a more practical issue, which is the communication challenges. And I hope after the talk, you will get your own idea how to tackle your own problem. So now let's move into the first topic of the talk. How can we design scalable reinforcement learning for general multi-agent network systems? I will give a quick review of reinforcement learning. So recently, we have seen many news about reinforcement learning, like the IO outperforms human in Go, and IO outperforms humans in video games. The successful stories are very impressive because for these problems, the online model is unclear. But the RL can learn a good control policy by only observing the state and reward, and by keeping playing the game over and over. However, in the meantime, there have been many discussions and critiques of this model-free IO method. So first of all, The recent success of IO heavily depends on the large amount of data and the powerful computation. It is very hard to imagine how to scale the method to large networks. Secondly, most of these stories are empirical results. There is a lack of provable guarantees, which is a big problem for safety critical networks. So the challenges motivated us to ask this question. Can we extend IO to network systems and still have some provable guarantees? So I will present some positive answers, but the key is not to just view the network as a big black box. The key is to explore the network structure. What is the structure we're going to explore? Let's dive into some details of the problem setup. So we have a group of agents. As each time, every agent has a state, action. And we're going to consider a tabular MDP problem in this part of the talk, which means the state and action are finite. At each stage, the state is updated according to the local transition rule. So what this rule has been saying here is that for an agent, I, so his next state will depend on his current state, his current action, and also the neighboring state. This local transition rule defines the local physical network. And in the learning, we assume we don't know the specific state transition rule, but we assume we overall roughly know the network structure. At each stage, every agent observes a local reward, which depends on their own local state and action. The goal is to find a control policy to maximize the long-term expected reward. Here, the policy is a stochastic policy. And the objective we are going to consider is a discounted long-term reward. And it definitely can extend to the limit averaging case, but for the simplicity, let's focus on the discounting case. So now let's look at this MDP problem. When we try to think about how we can solve this problem, the first challenge is the curse of dimensionality. The size of the problem quickly blows up with the increasing number of the agents. So even if individual agents had a small number of state and action choices, the joint state and action profile takes an exponential number. As a result, the standard MDP or IO methods cannot be applied. Of course, people have known this for a long time, and there are nice papers study the computation complexity of such problems, and people notice that it's fundamentally intractable. So people have been trying to develop different methods for scalable solutions. And for example, we can just treat individual agents as independent learners, or we can use different parameterization to reduce the dimension of the problem. But overall, it's just very hard to analyze the optimality guarantee. Besides this challenge, the next challenge is the information constraint. So suppose there's a magic learning method which gives us an optimal global policy, but when we try to use the policy, we notice that it's near the global information, and which is very hard to obtain for everyone. So this motivates us to consider the local policies where agents making decisions based on their local observations. And here we focus on the extreme case, really just based on their local state. And we know that it actually can be extended to local policies, including the neighboring information. So however, even if we only aim at learning the fully local policies, because the coupling state transition rule, so agents' local policies will still affect each other. As a result, during the learning process, we still need communication to allow them to coordinate to find the best local policies. So in summary, what the problem we are trying to solve is this. Given this network MDP problem, how can we use the local state reward observation plus neighboring communication to find a good local policy? I highlight local here because it's going to be defined later on. So how are we going to solve this problem? First, in case you are not familiar with the RL literature, I'm going to give you a quick review of some RL methods. In particular, the policy gradient and active critique. So we start with a parameterized policy, and here the parameter is theta. given our policy, we can write down the long-term reward as a function of the policy parameter theta. So then from optimization point of view, we can take a gradient step to update my parameter theta. But the difficulty is how to get the gradient information because we don't know the state transition rule. So fortunately, there is a nice theorem that connects the state reward with the policy gradient, which is called the policy gradient theorem. That's formally listed in Sutton's 2000 paper. For those who are not familiar with RL, please don't be intimidated by the notations. So the important message here is that we can have, if we have Q function, the state distribution give under a policy, and then we can estimate the policy gradient. And what the Q function is, the Q function is just expected long-term reward given a state action pair. So people sometimes also refer it as a Q table because the state and action are finite. So once we have this theorem, we can design different learning algorithm. And this is the one popular RL method, active critique. And roughly the learning method follow this framework. At each active step, which is also the policy gradient step, the learner is going to update the parameter theta according to the policy, estimated policy gradient. And then during each critique loop, the learner is trying to estimate the gradient by estimating the Q function. And how to estimate the Q function is try by observing the local state, local action, local reward, and using some learning method to update the Q function. And one popular method people have been always using is the temporal difference learning, like we usually refer as the TD learning. So this is the overview of the general method here have been used. And we notice like this is a single agent for information case. And what's the problem for this method? When we look at the Q function, so the Q function is a big Q table depending on the joint state, joint action. So it's going to be very large. And it's also need global information. So let's dive into the details of the RL in our network setting. As I mentioned before, we are only going to consider the local policy. So we can parameterize individual's choice as the theta I. So now the global policy is the joint profile of the theta. And we can substitute the theta to our Q function and to see what we have. Not surprisingly, the Q function is going to depend on everyone's state, everyone's action. But recall that now my reward stage reward is the summation of individual reward. If we just substitute this stage reward into the Q function, and by simple algebra, we actually can define something called the individual Q function. But because the coupling through the state transition rule, even we call it as individual Q function, the individual Q function will still depend on the global state and global action because everyone's action will still affect other people's long-term reward, which is a Q function. So therefore, this Q function is still exponentially large. Now, let's look at the policy gradient. So because now we only consider local policy, so each agent only needs to have partial gradient. But even it is partial gradient, when we write down the partial gradient, and we notice that we still need to do some global summation using the global Q information. So this is two challenges. Like we still have a very large table, and we still need a global information. We need to know everyone's Q value. And how are we going to do it? So in summary, as I showed you before, even we have this local Q function defined, but it's still exponentially large. Individual agent I still need to know everyone's Q function. So what we should do next? So normally I will ask audience to think and volunteer, give us a few options. But here I will just give you probably half a minute to think about what you are going to do next. So what exactly I mean asking here is this. So imagine you are the agent I, and you are at a big network. So you only see yourself, some of your neighbors. It is very hard to know what's going on with people that's really far away from you. So what you should do? How can you evaluate the quality of your local policy? And how do you know your long-term expected reward, which is the individual Q function? Okay, I guess you might already have your ideas already. So there are definitely many, many ways to do it. And the method I'm going to present is actually very straightforward and you can say lazy one. I will just do truncation. So since I can't have the global information, I will just ignore the people who are very far away from me. And I will keep a small table based on my K-hop neighbor. And how big the K is, depending on yourself. So I know you might be thinking, aha, are you sure? Is this going to work? To be honest, I was surprised when I first saw this idea too, but surprisingly, it works. So why it works? Because we have very nice property of this network MDP problem, especially exponential decaying property. So what the exponential decaying property means? It means that if an agent is very far away from another agent, then this agent's state and action has a small effect on the other person's Q function, which is the other person's long-term expected reward. And the further the two agents are far away from each other, the effect is smaller. And the effect decays exponentially fast as the distance between the two agents getting further. And surprisingly, as I said, the MDP problem I showed you before have this exponential decaying property. And doesn't matter what the network structure is, what should be the discounting factor, and what the mixing rate is. So what does it mean? It means now at least we got the one problem solved. Our big Q table now become a smaller one. And because the exponential decaying property, we can show this truncated Q function is actually a very good approximation. So now let's move to the gradient step. So for the gradient step, as I said, for the full policy gradient, the full partial policy gradient, we need global summation of everyone's Q function. So even now we change the big Q table to a smaller one, we still need to do a global summation. So what should we do? As you notice here, I ignore the people far away from me again. I'm just going to do local summation. Is it going to work? Yes. So because the exponential decaying property I showed to you before, and also because of some other properties from the network MDP problem, we can rigorously show that the truncated policy gradient is a very good approximation of the full policy gradient. And as I increase my neighbor to consider, my approximation can get better. And the improvement is exponentially improvement. So now in summary, what I've been showing you here is we have the truncated Q and we have the truncated policy gradient. And it's very natural to see how we're going to extend our method to develop scalable RL for network system. And I'm just going to show you the high level idea now. Going to be the active retake method. I'm going to compare with the full information centralized case and the individual, the scalable case. So for the policy gradient step, instead of using the full policy gradient, I'm just going to use my truncated policy gradient. And the truncated policy gradient will depend on the local Q function. So instead of to estimate the full Q function, I'm going to estimate my truncated Q function. And since my truncated Q function only depends on my neighbor state action reward, I can just use my local information to get an estimate of my truncated Q function. And you can see this method will be scaled up to any kind of network, and the complexity is not going to blow up, even if you add in more agents to the system. And in fact, we can rigorously prove the optimality guarantee because of the exponential decaying property. So we can show that the sample complexity is not going to blow up with the increase of the network. So here for the upper bound, we have two components. So one component related to the learning rate is will eventually come to 0. And the other part, the steady state error that's caused by the truncation. If we care about the truncation arrow, like we can just increase in the number of agents, but you can see the improvement is exponentially fast. And you can see the numerical result. We have tested the algorithm on different cases. And here is one example of multi-access wireless communication problem. So in this problem, users have packages coming randomly, and they need to send the package through the access point. But if two users send the packages to a same access point at the same time, the package will be dropped. So we run our algorithm on this problem, and we compare it with the benchmark algorithm, which is called Aloha. So for this simple set, you can see our approach can outperform the benchmark. And the benchmark actually using some parameter from the system, but our method didn't using any structure of the problem. We only using certain network connection structure. But of course, you can also see there's a lot of room to improving our result. Like the learning rate is pretty slow. And this is principle because we are still kind of follow the model-free IO method. And the sample complexity is always a critical issue for those model-free IO methods. So right now we are working on combining the model-based and model-free method to further improving the learning speed. So in summary, I've showed you how we can use the network structure to design scalable reinforcement learning methods. And the key is to use the network structure to design the truncated Q-function, truncated policy gradient. And our method doesn't need to know the system dynamics and scales up to large networks and have very strong provable guarantee. So lastly, I want to highlight that the framework is actually very general. It can be extended to different networks, different IO methods, including both model-free and model-based methods. And these are some ongoing work we've been working on recently. So now let's move to a more concrete topic, a more concrete network, which is power system. To give a quick introduction of power system, the goal is to make sure supply will equal the demand all the time. So traditionally, the control has been done in the supply side. But recently, there are a lot of new elements in the system. First, we have renewable energies in the supply. And in the demand side, we have smart appliances, we have battery, we have electrical vehicles. So together, people call this new generation and demands as distributed energy resources. These distributed energy resources have a huge volatility, causing difficulties in the traditional control, especially the frequency control and voltage control. To show you an example, so this is a frequency behave when there is a sudden drop of two nuclear plants, which is only 4 to 5% of the total generation in ERCOT. So you can see the frequency drop quickly, and it takes more than 10 minutes to drive the system to make sure the frequency comes back to the nominal value. And you can imagine the situation will only become worse once we put in almost 50% of renewable energies into the grid. And similarly, the voltage control face similar challenges. And this is a one real demo that was done in Texas. There are 100 homes, and all the homes have rooftop PV. And you can see in the middle of the day, because of peak PV generation, the voltage went up to a big degree. So now all those challenges motivate us to consider alternative solutions. And one nice solution is try to using our smart appliances, try to do load control. So there are many advantages to do the load side control. For example, because they can react very fast, and the load is not going to cause any additional emission. And it has a very large number and has the potential to localize the disturbances. In fact, in the existing electricity market, the load control has been applied, but they are mostly being done in the slow time scale market, such as day-ahead market and hours-ahead market. So the question we have is this: can we control the load quickly and to making sure the frequency voltage have been maintained in real time? So I will focus on the frequency control to illustrate our overall idea. So let's first take a look at the system dynamics. So in power systems, so we have buses that's connected through transmission lines. Each bus, the frequency is governed by the power generation, frequency-insensitive loads, frequency-sensitive loads, and power flows among connected buses. So when there is disturbances, either in the generation or in the load, the frequency will change according to the swing dynamics. So once the frequency changes, the phase angle will change, and thus the power flow will change, which will affect the frequencies at other buses. So here I provide a simple linear approximation to capturing how the power flow will change when we have the frequency change. Even we develop our theorem and algorithm on this linear approximation model, we will test our algorithm on fully nonlinear model, and you will see it will still work. So to recap, we have a system network dynamical model describing how disturbances affect the frequency over the entire grid. So when there is a change in the system, say in the generation, we would like to control our controllable loads to make sure the generation and load are balanced all the time, and the frequency variation can be small, and the load discontinuity can be minimized. As you can see, the language I'm using here, we can model this problem as an optimization problem. So here, this is a mathematical model for our optimal load control problem. So we can use the constraint to stand for the power balance, and we can put in the frequency variation into the cost. We can put the discontinuity into the cost. So in case you are lost by these power system details, let me abstract everything and discuss what's going on with our problem. First, we have a physical dynamical system, and we have an approximate model that's describing how the disturbances are going to affect the system state. And the disturbances usually is very hard to measure in real time. So the question we want to ask is, can we design distributed feedback controller to make sure the new state is going to be an optimal solution of some interesting constrained optimization problem? And we hope the controller U is a closed loop U, which means it's only depending on the measurable state. So you can see the problem fits to the classic decentralized control framework, and thus it's very hard to solve this problem in general. So I'm not going to show you details how we derive our solution. Instead, I will just show you the solution. For our low frequency control problem, the control rule is actually quite simple. For each load, measure the local frequency and update its new load according to his own utility function and the local frequency. So you can see it's fully local, just using the local information that he has. So despite the simplicity of this control rule, we can rigorously show that it converges to the optimal solution of our optimal load control problem. And how we really prove it? More surprisingly, despite the fact that we don't have any sophisticated computation in this our load control, our system dynamics plus the load control together is actually exactly an optimization algorithm for our optimal load control problem. The system dynamics here turns out to be the dual dynamics of this optimization problem. So what this means is that our physical power system is serving as a big computer naturally. It's not just sending power to us, it also carries so many information for us to use to decide our local control policy. As a result, so we don't really need additional sensing about disturbances, we don't really need many computation, and we don't really need much communication to compute the optimal solution of our optimal load control problem. We can just rely on our system dynamics to tell us what we should do. So see what the implication for the implementation. So when there's disturbances, the frequency will fluctuate, and each node can measure the local frequency and using the local frequency to update the loads, and which can keep the system balance and frequency variation small. So here you can see the frequency kind of serve as a coordination signal, like the price of imbalance. Because of this, for this framework, we actually even don't need a communication. And we can see how it's performed in the high fidelity simulator. So you can see with our additional load control, the frequency variation is much smaller and the system can react much faster. So in summary, what I've shown is that we can connect the physical system dynamics with the computational optimization algorithm. So based on this connection, we can design local control rules and provide very rigorous convergence guarantees. So moreover, this framework has motivated many recent research activities in both application and theory side. So here I list some applications that I'm very familiar with. It includes secondary frequency control, voltage control, optimal power flow, and green building controls. In the theory side, first, people trying to understand what is exactly going on with this framework and trying to identify the sufficient and necessary conditions. And people also trying to work on extending the framework to more general problems, so which will open up for new applications. And lastly, because of the success of the primal dual algorithm, there is a resurgence in studying primal dual gradient dynamics, trying to figure out the global convergence and the global convergence speed. So to show you, to give you a little bit more examples to convince you this is a powerful framework, I will focus on frequency control and voltage control. And also I want to bring the communication back into our discussion. So for the secondary frequency control, rather than just keep the frequency deviation small, we would like to keep the frequency around the nominal value, and which is 60 Hertz in the US. For this problem, we have shown that communication is necessary. But we can still apply our original framework by just adding the local communication, and we can drive the system frequency back to the nominal value. Again, we build our solution based on the connection between the physical dynamics and the optimization algorithms. And we show that the physical dynamics plus the local control plus the local communication is actually a primal dual gradient algorithm for an optimization secondary frequency control problem. Besides the frequency control, we have successful stories in voltage control as well. So we designed distributed feedback voltage control according to similar principles. And we can show that our distributed voltage control can keep the voltage with acceptance rate almost all the time. And here is a simulation that we simulate the control for entire day, and we simulate the control in real time. Again, I would like to highlight that the simulation was done using the full nonlinear power flow model, and we even simulated the three-phase unbalanced case, which have some nice performance. So in summary, for this part of the talk, I've shown that we can connect the physical dynamics with optimization dynamics by understanding the physical dynamics from optimization point of view. And based on this connection, we designed distributed feedback control rules to maintain the system's optimality while satisfying the important physical constraints. So the method has many advantages. It reacts to the system disturbance quickly, no need to know the exact disturbance level, and it is distributed and has strong provable guarantees. But as shown in these applications, we see that communication is important for coordination. So when we talk with the power engineers, the power industry people, we often got the feedback like this. Your algorithm looks nice, but the reality is that we don't have real-time communication in the existing power distribution network. Therefore, we are worried if the communication will go wrong and how to rebuild the communication, and what if some people are going to hack the communication. So this motivated my last part of the talk is how we can try to reduce the communication needs of our coordination rules. As I mentioned, communication is necessary, and that have been discussed. The communication has so many different challenges, no matter what communication technology we're going to use. So we ask this question: can we just reduce the communication to a minimal amount? So The limited communication control has been studied in our control community, and we know it's very difficult when we consider the interaction between the feedback control and the communication complexity. But here, I'm going to take a slightly different perspective. First, I'm going to consider a very general description of distributed coordination, which can capture most distributed iterative algorithms. So we have a group of agents, and each agent will send information to his neighbors, and in the meantime, also receive the information. Once I receive the information, I'm going to compute what the next state I should be. And typically, in many iterative algorithms, like we often have some nice properties. And for example, like we will start with some algorithms that will convert to some good stationary point. So if you keep compute, and until the system will reach certain stationary point. So this is a very general iterative framework. It's almost capturing a lot of distributed coordination algorithms that people have been used. So the challenge here is because of the limited communication, we are not able to stand the exact communication C. So we're trying to think about what's the quantized information I should send. So we're going to consider quantized distributed algorithms. So for the quantization distributed algorithms, I want to highlight that it's not just a problem for our control community. And there are a lot of work I've been doing in the computer science and machine learning community, optimization community, because motivated by the big data, communication now become a bottleneck to speed up the process. So there have been a lot of recent work have trying to ask similar questions. What's the quantization, or what other communication schemes that I should use? Not necessarily going to be the quantization. But I'm going to focus on the quantization for this public talk. So let's come back to this problem now. Because I cannot send the exact information of the C, so you can imagine the trajectory is going to be different. But if the quantization is done properly, the overall direction should be still good, and it still has hope to reach to the same stationary point, at least with a high accuracy. But based on the discussion, it's actually easy to get this kind of high-level intuition. So if I really want to get to the exact same stationary point, it looks like I need to improve my quantization quality along the way. Because at the beginning, since I'm very far away from the stationary point, as long as my direction is right, I'm okay. But once I'm getting closer to the stationary point, any small arrow might lead me to different direction. So here is one question. Does this intuition mean we need to increase our number of communication bits? I will show you that it's actually not necessary if we really take advantage of the properties of the original distributed iterative algorithm. So what are properties we can consider? There are many candidates, so such as smoothness, convexity, convergence rate, and others. If we can harness those properties well, we probably can have very efficient communication schemes that can allow us to still have the convergence. For example, if the original algorithm is smooth and has linear convergence, then we have designed an adaptive quantization scheme which only uses a constant number of bits but can maintain the original linear convergence. For those who are not familiar with the optimization language, the linear convergence here in optimization actually corresponds to the exponential stability in control, and the linear refers to the log scale. I'm going to give you a quick idea how did we do it. So, like to understand this adaptive quantization, let's first look at the non-adaptive version. So quantization usually, like how people usually do the quantization, we're going to use the grid. And for given information that I want to transmit it, because of limited communication bit, I can only take a vertex that is the closest one. And for the next step, I have a new information I need to send. And then I'm going to grab the closest point from the grid. You can see here, because the grid is stationary, I didn't change anything. So the quantization quality is now improved. So as the algorithm goes on, it's very hard for me to really reach the stationary point exactly. And how we can improve the quantization? How can we improve the quantization quality? So like one simple idea is, hey, probably I just need to increase my communication bit. In that way, I can improve in the resolution of my grade, and I can get better quantization. But you can see that really needs increasing my communication bit. So I'm going to show, like, if my problem is smooth and linear convergence, it's not necessary. Why? So we know the algorithm overall is heading to the right direction, like to the saving point, because of the convergence. And also because of the linear convergence, so we know that if I design my quantizations well, so the distance between the new positions, xk and xk plus 1, is getting closer and closer because they are getting closer to the saving point. So correspondingly, because of the smoothness of the algorithm, so my transmitted information, the ck and the ck plus 1, is also getting closer and closer. As a result, we actually can move our grade to focus on the new position, the new information. And since everyone has the qik from the previous communication scheme, so we can move the grade to center around the qik. And in the meantime, I can shrink my grade size because my new information ck is actually getting closer to my last ck information. So once I shrink the grade size, and I can improve my quantization quality, as long as when I shrink my grade size, I still cover the new information that I need to transmit it. So you can see this is actually a very simple adaptive quantization scheme. But based on this quantization scheme, we can show rigorously how the quantization degrades the algorithm performance perfectly. So I'm only going to show you a simple numerical test we did. And from here, you can see we can keep using the constant number of bits, and we can maintain the linear convergence. So look at here, it's a log scale, and that's what people refer to as the linear convergence rate. And once we add a little bit more communication bit, it almost recovers the exact same convergence behavior as unquantized version. So let's come back to what does this imply for our practical application in stable physical systems. So come back to the power control problem. In order to reduce the communication that we're going to use to coordinate the different devices, so I will often suggest start with a fully decentralized case that is no communication, and then study the limitation for the fully decentralized case and trying to add some local communication to make the system control better. Once we have the local communication, then we'll apply the quantization scheme that I showed you before to reduce the communication. And once we reduce the communication, it will open up many different technologies, communication technologies that we can use. And it can robustify the coordination to communication failures. And for example, we probably can just use the power line communication to coordinate the devices as a distribution network. So if we follow this flow, ultimately, our coordination scheme could be more reliable, more secure, and easier to deploy. So now it's ready to conclude the talk. In summary, I've shown you 3 examples on how to take advantage of different properties to develop scalable solutions, starting from the general network system to more concrete power system to more practical implementation issues. As you have seen, the problem is big and challenging, and different systems might require different perspectives or need to combine different perspectives. I also want to highlight that in reality, the problem is actually much more complex. There are often humans in the loop, and there are different time scale and different spatial scale intertwined together, calling for systematic architecture design, like the hierarchical layering structure to allow region-to-region coordination. So to tackle these problems, it requires close collaboration between theorem, algorithm, and applications. So closing the loop between the theorem, algorithm, and applications is the only way to realize the next generation of smart systems. And that's the only way we can actually really harness all the connected smart devices. And I hope my talk can give you some fresh perspectives and convince you that this is actually a very exciting area to dive into, and this is the right time. To close, I would like to thank everyone again, and thank you for watching this video. Again, feel free to contact me in any way. I hope you and your family stay safe and healthy, and hope we will see each other in person at next ACC.
Thank you very much. It was an excellent
Thank
talk.
you, everyone.
Very inspiring.
And thank you for the questions. All the questions are very inspiring. Is there a way I can just record all the questions?
I think so.
I'll try to download the log files for this.
And
great, thank you.
Send it to you. So we still have a chance for a couple of quick questions if anybody has it, because I know you answered a lot of questions on the fly here, which is really nice. So very helpful. That one advantage of the virtual thing is that you can actually answer questions while it's going on. So anybody has any other questions?
Looks like there's an open question that just came in.
Okay.
Oh, nope, just a comment. Yeah.
Oh, okay. Nice talk. I guess that's good.
Yeah, thank you. Yeah, so can I add a few sentences if no one asks questions?
Please.
Yeah, I think based on the questions, there's a lot of interesting excitement about how we're going to dealing with the network case. And for the first part of work, I want to say I picked a simple story to give the talk. I probably that is the one for everyone to understand roughly what the framework. And for our recent work, we have been extending similar idea to more complex case. And when we try to extend to more complex case, the two directions have been taken. So one direction, we're going to focus on still the general modeling. But then for the other one, we've been really looking to more specific applications. For example, for the robotic swarms, and for the power system, and also for the networking, the computing networking. So because each problem will have their own property, then telling us, okay, what kind of truncation we should do? Probably truncation not the right way, because besides the truncation, I should also develop some other communication, just sending some very critical information to someone. Hey, tell them there's some like failure in this system. Everyone should do some precaution. So that's like, but we have been trying those, and I think all the questions you guys have been asking, every direction is worthwhile to see, like which one is better. But that's truly what depending on the application or what the system we've been talking about. Yeah, that's one comment. I think I have one question here. Organization. Yes. Yeah. Great. Yeah. I think the comment by Bob Bateman is a very nice comment, and I can also add in a few sentences for that part work. The limited communication work, as I mentioned, the motivation for us to start it, we actually started that work 6 or 7 years ago. It's really because the frustration of the collaboration with the power industry. Like I have been keeping saying, you just need a local communication, you can achieve many in performance. But then the reality, like if I think about my home, my device is not talking with any other person's devices. So it's very hard to implement. So then at beginning, we started thinking about, hey, can we do power line communication? What is the limitation? So then we try to reduce the communication, like do the quantization. And once we started doing that, then we found computers, like first control computer have been working on that. And on the other hand, very interesting, I think in the past 3 to 4 years, so especially in those optimization, computer science, community, machine learning community, there's a lot of excitement or similar problems. They also try to reduce the communication. So the quantization scheme is only one method. If I really want to reduce the communication, think about each time when I send communication, it's also a vector. It's not just like one number. So if I'm sending a vector, so the first thing probably besides do the quantization, what I can do is I can think about which dimension is the most important thing I should give. So so that will also motivate different kind of like limited communication algorithm. So once I have been doing that, I can also further think about, can I even further to just sending a few bits? And that's kind of my understanding of what's going on with the, like, not just control community, the machine learning community, like putting all these things together. It's a very interesting topic when we really try to understand what's the algorithm we're trying to reduce communication, because different property will tell me which one is better to reduce. And like, thank you for the comment. Santosh, I think you are muted.
Right, indeed. So thank you so much for the talk. So I appreciate it. And I'm sure you can answer questions through Slack and emails and all that too as well. We do have an award ceremony for the Best Paper Awards and the RI talks at 12 today. And then there's a closing reception at 6:15. You have to bring your own drinks though, but we'll be virtually. So thank you again for the talk. And next, I guess we have the posters will be starting right now at 9 o'clock. So thank you all very
Great.
much and talk to you
Great.
later. Bye-bye.
Thank you. Thank you, everyone.